All right, as you see, we are recording this. I will upload. Everyone here have access to my playlist, right? On YouTube? Yes, no? Okay. Uh, you should not say no. I'm pretty sure you have it. You've been taking too many of my classes. You forgot about it. Okay, I'll post the link. Um, so as I said today, actually there's a bunch of people joining online. Karan say hi from online. Um, we will continue on with the quick announcement. Next week, it turns out there's so many holidays next week, which kind of surprised me. We're gonna we're not gonna have class on Thursday. Luckily, I think Tuesday is not a holiday, unless I'm wrong. If I'm wrong, let me know. But definitely, I think Thursday is a holiday. Friday, I think the government announced like another holiday. Why are we having so many holidays so close to election? Um, but what we would do is I will need to figure out a makeup class. I would try to make it such that it's on the class that doesn't matter too much in case you cannot make it. And we'll do the recording like this setup. All right. Let me know if any of you have any preference on when. My quick question is, do you want that to be earlier in the semester, later in the semester, or in the middle of the semester? Because my impression is when it's closing to the final, you guys are like doomed with all the homeworks. So maybe a makeup earlier in the semester might make more sense. If that's the case, let me know. Any quick vote here? Early? Okay, 1, 2, 3, 4. How about 5, 6? Anyone online want to do early? Okay, early online as well. I'll say one. I'll just assume that those two early represent everyone online. Democracy in play here. Okay, at least there's 3 of you guys online saying early. Okay, let's do early. I'll try to do it not the week after, because the week after I'm pretty much fully booked, but maybe the week after that. So it's week 4. By week 4, we should have some day that we'll do a makeup class. All right. Um, Now, how many people heard about this thing called Moore's Law? How many people heard of this company called Intel? All right. So Gordon Moore is one of the basically is co-founder of Intel. He co-owns the company. He was also working as a CEO. Basically, he's their boss for a long time. Um, they changed the management and the CEO and quite a lot, right? But Intel is a really old company. But one thing Gordon Moore said is that um, if you look at the number of transistors that you can put on a chip and you plot the trend, if you plot the trend, you see, right? You see that it double every after some certain time interval, right? So on the y-axis here, you see there's a log scale of the. In this case, it's calculation per second, per $1,000. Basically, if I throw in this much money, how much calculation can I do from my CPU? It's as simple as that. I buy a CPU with $1,000. How much performance in terms of calculation can I get? And as you can see, it's like pretty good trend, right? It's a log scale. So you can see that it's actually going up quite fast, right? This is where. So I think I asked you about like, have you seen the movie Imitation Game, where they built a machine to crack the German secret code, right? What I just circle is the machine around those days, and look at where we are, right? Your phone actually is much more powerful than the computer we used to go to the moon, right? So we are actually on the days where our computational power far exceed what our parent generation can do. Not sure what we're doing with computer nowadays. We're doing some useful thing and we're doing a lot of fun and useful things as well. So I will not judge anything that we do, but you can see that the trend's going up. What's the problem? What's the problem? What if I tell you there's this thing called physics? Right? So electron, even if you look at electron, they have a size, right? It will occupy some space for sure for the electron itself, right? Which means that at some point you make a transistor go smaller and smaller and smaller, what happens? You ended up cannot put any more electron in, right? It's too small for my electron. So it ended up maybe holding just a few electrons, right? If it's holding just a few electrons, how can I detect is that a voltage of 0 or non-zero? It's going to be really hard, right? So these days, like today, 2023, and I'll actually, to be honest, I'll tell you since 2015 onward, this is one of the big problems in computer engineering, where this thing gets way too small. What do we do? How do we keep making small things? How do we keep pumping out new generation of processor that is faster than the previous year? Right? I mean, think about it. What would happen to Intel if the next year they have a chip and it's the exact same speed? Will you buy the new chip or you're gonna pick the old one? Right? So there has to be some features around it. It's like, can you get more performance? So that's Moore's law. And this thing changed the way we design the computer and it changed the way we design systems. The second thing is what we call Dennard scaling. Dennard scaling is when you make the computer get smaller and smaller, right? What people assume is with a smaller component, let me see a show of hand, who think if we have a smaller transistor, who think that we actually have a machine that consumes less power? We do, right? It makes sense. My component is smaller. If I have to drive electron from one place to another, it's shorter distance. Everything operates maybe at also lower voltage. So I'll be more power efficient. Turns out there are things like when it gets too small, you have leakage. Leakage is when my circuit doesn't do anything, it has to burn power. So that these kind of thing where power doesn't scale as much anymore, which affect things like my phone, right? Because if you want to design a good phone, well, I'll define a good phone, which is a phone that would last you a day without a recharge, right? You want to be able to like go around your day, don't have to worry about like plugging in, right? How many of your phone can do that? One, okay. What a rich guy. No, I'm joking, but if your phone is like 3 years old, right? If let's say your phone is 3 years old, you will notice that you have to plug in the middle of the day because the battery run out. If you play any game period on a phone, you might also have to do that, right? It does consume more power. So this thing also becomes a big part of your system design. Let's say you have to build Android. Android will have to be more power efficient than what? Linux for the server. Linux for the server also should be really power efficient as well because you don't want to power your data center with a nuclear reactor. It costs a lot, right? So power becomes another big aspect of system design these days. There's also hardware changes, right? So if you took my fun part class, you've seen this already. Basically, this is an image of your chip, your CPU. Look at what's in them, right? You might have looked at that and see something that you saw before, the ALU, right? This is where the brain is. That's where you do the add, the subtract, and everything. Any observation from this diagram? Rephrase the question. Let me tell you, so that's the area of my CPU that I would dedicate it for my brain. What are the other things in there for? It's like many other things are in there, right? You have and anything that you've seen earlier. Yeah, Robert from the chat, thank you so much. He said that floating point operation also take a lot of logic, right? The floating point and SIMD. Why? So how many real programs require floating point operation? A lot, right? Compared to back in the day, well, we kind of realized, hey, these are important, so we will dedicate a lot of area on my chip for that. That's also the cache, right? I cache, data cache, the L2 cache, right? So it turns out to make it possible, well, obviously you need a logic to just run things, right? Then the decoder will learn more in the module 3 when we go into architecture, but these are what you need to understand your assembly. This is like the logic we designed. Remember system skill task 2 of assignment 4, the one that do like push with different pattern. That's what that hardware is doing. But for every single instruction for the Intel chip, for any chip, right? Data cache used to make your data access faster. It's like when you're hungry and you can always go to 7-Eleven rather than going to like a further, like somewhere further away, right? And you even have the level 2 cache, again, the cache, but even further away. Then people, well, I mean, we've been realizing that for a long time. I just never pointed out here. Where are my instructions? Where's my code? Where's my program? When I run the program, it's in the memory, right? What do we know about memory? Yeah, it's slow. So if you build something to make data access fast, you also need to access the instructions. So it makes a lot of sense to have also the cache for your program. We call this instruction cache, all right? Then you also have the branch prediction, right? This is basically where we try to guess whenever we have if else or for loop. Let me ask you a simple question. Let's say I have a for loop. What would be the likelihood of what do I do at the end of the loop? What's more often? Do I go into the loop again or exit the loop? Go into the loop again, right? So, I mean, you can predict these things based on history. That's a logic for that. That's also allow you to access the memory in parallel. That's the logic that allow you to execute many instructions at the same time. You don't do one line at a time. Now you do like 5, 8, or more. You also have a different logic for any fancy instruction that the hardware designer say, hey, people use this a lot. So instead of implementing this using software, let's just build the hardware for this. So as you can see, like your CPU these days also have the way to execute almost like a GPU. Almost like a GPU. It's not exactly the same. It's much more lightweight. It's much less crazy in terms of the complexity. Are you all right? Okay. So, here is what early OS would look like, right? It's going to be just a collection of runtime libraries, which would abstract away a lot of common routines. And the setting is going to be basically one user, one program. And you basically run that for days. Why does that make sense? Because hardware back then is super expensive. You build one. It's also really slow, so you run that one program for days. You don't have a lot of tools. Imagine the world without compile. Imagine, let's say you write a code, you don't have GCC. What will you do? Right? Because back in the day, we don't have that. We don't have an actual programming language until we have Fortran, which is like it takes a while, right? So when there's a bug, you also have to start over, which is annoying. I have a lot of respect for these guys. I'm like, I need to write a program. If there's anything wrong with it, I need to write the whole thing again. They can't, like back in the only they program with a punch card. It's not even a keyboard, right? That's what's more annoying, right? Then here comes the age of multi-user OS. So basically you have those old mainframes still, but the mainframe gets better, right? So One thing that we think, hey, it's a good idea maybe to share the mainframe because why? So expensive. This thing cost millions of US dollars back in the day. If I only want to run one single program, I'm not doing a lot with that, right? Why don't I share the system amongst many users and many programs? So the execution model becomes like I'm gonna have a lot of jobs that I want to run. The OS takes in all the jobs and figure out who get to run first, who get to run next, right? Then to manage the basically file through the IO or any like things that coming from the network, all those things, right? IO, input and output, like keyboard, even things like that, will work in the background using direct memory access. Basically, I have a way for my IO to connect directly to the memory. Why is that the case? I don't want to waste my CPU to handle IO. DMA is also being used nowadays. It's one of the common way you can allow data from your IO directly to be on your memory, to be used by the CPU afterwards, right? So the mainframe is going to look something like what I show you on here. DMA basically, you don't need to use the CPU to copy data for you. Coming from the IO, go directly to the main memory. And then when it's done, that's when I notify the CPU, say, hey, I'm done. Right? Simpler. And then this evolved into like multitasking, multi-programming, where you can run multiple tasks at the same time, write multiple programs. You might be surprised how many parallel programming paper and how many parallel programming hardware design are like in the 70s and 80s, because people are thinking, hey, maybe there's something we can do, right? Then afterward, computer have like one thing that happened to computers, it gets smaller, right? It gets smaller. So you have things like interactive timeshare OS. I can, well, back in the day, if I'm rich, right, I can buy this computer, put it at home. Only one person will be using it at the same time. That's why we call it timeshare. With timeshare basically means that one user who uses it at the same time, but you can share the computer with multiple users. Then it's more interactive. You have a mouse, you have a keyboard, right? Rather than programming using a punch cord or switches or wire directly going into the computer, now you have a keyboard, you have the mouse. You can also run multiple applications concurrently. And that's, well, because these are interactive, right? So the usage will be in burst. Whenever you run something, that's when you have a use. Otherwise, no one is using it, right? As opposed to mainframe back in the day where I run one single program for like days and days and days. It's different now. When you have different requirements, multiple things have to change. Hardware will have to change, system will have to change to make sure, again, so that you can make the right trade-off. What do you want to optimize for and at what cost, right? And these are some of the prime examples, Windows, Mac OS, and Linux. All right, now here's a side discussion that I added this semester, right? These things are interactive, right? You think about it, you have a phone, it's still one single user at a time, because only you is the person using the thing, right? But then you also now have many different internal hardware, right? Your laptop will only have a webcam. Your phone has a fully functioning, much better camera that also serves as a live video where you can actually open the camera and do multiple things, right? There's also what we call DSP processor, digital signal processing, which process a lot of like signal from your video, audio, and do a lot of fancy mathematical tricks to make sure the video is done correctly. You can do encryption, you can do encoding, decoding. You can also like hear the sound correctly, right? There's also like new things that came out for a while actually, but it's something that many people didn't realize is like things like security chip. We used to think about it this way. If I have a secure system, there's something in the OS I can trust. And we'll actually talk about this today, right? the lowest level of OS is a region where I should be able to trust them. Otherwise, the computer is not legit. Like I can't do it. But then, how many people actually try to crack a hardware or sideload a different like OS, jailbreak, iPhone? How can you trust those things? Where do you download it from? I mean, think about it, right? Those are built from, I mean, obviously it has to be built from some iOS source code, right? But how can you trust that the guy building that packages doesn't add more things that you did not realize? Once you install it in the OS, right? So there's also this concern where maybe we should not trust the OS. Maybe we should not trust the hardware as well. So let's build a security chip where some examples this chip would basically declare some part of your memory that this is the place I can control and only I can control. And I will not interface with anyone else. I will have some API for the application to use. I can tell who you are. So if you are legit, you can use this part. You can use them to store, for example, your password, right? This makes the whole security area much more like harder to crack, basically, because now you can't just hijack the OS. You can't just hijack and attack a piece of hardware. You have to attack the OS, attack that chip, which is not easy, right? There's also a machine learning processor, and there's a lot of emphasis on isolation. If one of your app crash, it will not crash. It will never actually crash another app, right? I rarely seen the case where one app crash and my phone crash. Right? It just turn off the app and you can restore it, and that's it. Right? There's also emphasis on resource efficiency because you don't have a lot of power, you don't have a lot of memory, right? If you burn too much power, yeah, that's it. Your battery is gone. You can't run anything, right? And then there's so many variants of the modern OS, as you can see here, right? And if you think about the history of that, right, you can see that there's history from like the DOS side of things, which is influenced by MVS and then VMS and back in the day, and some of these kind of influence into like the VMware, which allow you to do a lot of virtualization on an enterprise scale, right? And then on the right side, it starts with like Multics, which evolved into Unix. And as you can see from Unix onward, it becomes like many major things like VMware, Android, Linux, iOS, right? If I'm gonna modify this, it's like, well, we still use like Linux. Yeah, it's all kind of Android is also like influenced by many things, but it's kind of spawned off from Linux, right? And now with multiple type of hardware that are coming out, right, the OS is going to be much more complicated. Some of them might have to work with a much larger scale computer. It might have to work with a different hardware abstraction. These days, there's a lot of research that go into, hey, should we just think about the hardware as I have a CPU, I have the memory hierarchy, and that's it? Should we think about the hardware setup where CPU can be here, memory can be here, and have a bunch of CPU memory, and they're all connected? Become disaggregated memory or chiplets, right? These are actually would allow you to make even faster hardware. But the hardware looks so different, so you have to rebuild the OS for these guys, right? Might have to work with new abstraction, right? Serverless model like Amazon Lambda. I'm not sure if you heard about it. Basically, it's allow you to run a function. Say, hey, this is a function I want to run. Launch it. You don't have to configure the hardware. They kind of figure out how to run it. Then you got the output, right? It makes cloud programming in theory easier. It also means most of the tasks rely on the OS, so you have to do more things, right? You also have to work with new environment, right? Things like what if you have a bunch of drone? Anyone seen like a drone firework at like sports events? Looks kind of cool, right? But think about it. How do I coordinate everything? That drone has to go up like 1 feet, going to the left 3 feet. Wow, the other drone go that way. How do I do that? It's not easy, right? You might have to build a system for these things, right? Self-driving car also, there are new, well, actually not new requirement, but some certain things have a much more strict hardware, not hardware, deadline, right? If I'm running at 100 kilometer per hour, and then there's something in front of me, right? I better be able to detect what's that object by the time I hit that thing, right? Is that just a sign on the road? Is that an actual human? Is that a car also moving at 100 kilometers per hour, which means I don't have to dodge it. So I have to be able to detect those things within a certain deadline, right? Any questions before we move on? Okay. All right. So shall we take a quick break before we transition to the boot process? Because we're switching topic a little bit. So let me pause the recording. Let's do a quick break here. All right. So here is the boot process. All right. So we'll start with BIOS. What is BIOS? So BIOS, actually we'll go into more detail. But when you power on your computer, right? The first thing that gets run is whatever is on the BIOS. Then most of the thing that BIOS doing is checking the health of the hardware. Can I turn on? That will pass the execution on to the next step because it's the first stage bootloader, which will do some really, really primitive things, followed by the second stage bootloader, which do a little bit more things, which then boot up the kernel. So we'll go into more detail on what happened in each step, right? Because after that, you have the init process, which basically start everything that the computer has to start, right? Again, the state is from power off. You have to be at the state where all the service are either on or ready. Basically, you can use the computer from nothing to the state where you can use the computer. By use, I mean I can run any program afterward. All right. And the key idea is I will develop a set of steps. I will develop a set of steps that I have to follow, right? To make sure that I can effectively be in the state that I can run anything, starting from nothing. The boot process, BIOS, actually stand for basic input-output system. What is the basic input-output system in your mind? Keyboard, monitor, right? If I can interact with my computer with a keyboard and something on my screen, should be good enough. What else? Well, if you hear the beep sound when you turn on a computer, that's also a part of the BIOS job. So to do this, imagine again, right now, every single program is on your hard disk, not ready to run because they have no way to run it. They don't even know. Like you turn on a machine for the first time, think about it, it's dumb. It doesn't like wake up like no one command me to do anything, so I'm not going to do anything. BIOS will be the first set of commands. Is written in the ROM read-only memory. We call it EEPROM. That's an area in the motherboard that would have the init code for you for just for the BIOS. What it does is it will first perform pause, which is if you've seen the word pause before where you turn on the computer, stand for power on self-test. I turn my computer on, I test the hardware. If everything is correct, I just beep and then go on. If something is wrong, there'll be a different tone and hopefully you never have to hear it. I heard, for example, a different tone a few times before where there's actually the little battery that power, I think, the clock of your motherboard. That can go off. Basically, it just run out of battery, so I have to switch the battery. Then at that time, I hear different beeping. All right. And then this is making sure the hardware is ready and initialized. All right. And then I would set up a really basic services, keyboard, screen, the clock, and everything else, so that I can start to even consider running. Right. And that's it. That's it. All right. Any question on the BIOS? It's basically, hey, hardware, are you guys ready? That's all. Right? And then I'll go to the first step by, first of all, I have to talk about interrupts. What are interrupts? These are things that are coming from the hardware. Things are coming from the hardware. And it's allowed the hardware and software to talk to the CPU. CPU can then react to the interrupt by, for example, pause what it's doing and jump to a handler. Are you guys familiar with exception in Python, like handling divide by 0, right? Try catch. Okay, so think of interrupt almost as the same thing, but it is triggered not because something happened to the program, but it's from external source. Like I hit something on the keyboard. I typed something on my keyboard. All right. And after I handle the interrupt, I would resume execution. And here's how I would handle interrupts. Inside the BIOS would install some basic handler. You can check the interrupt list on the link, but here are something I'll show you, right? Interrupt will have number tied to that. Then with the number, there'll be the location, that's the address of where do I need to go to do certain things. So if it's action number 1, I will go to address 2000 and follow whatever's in that code and run it. So if I have this table and I boot my computer, now I have the basic way to install primitive function. Think about the handler as some simple function that I can do. And based on the signal, I run this function. If I got the signal, I run this function. If I got the signal, I run this function. All right. And if you want to go crazy with this model, I mean, you can basically implement, for example, printf in that area 1000. Why not, right? Would that be useful when you boot things? To be honest, yes. So you can print something on the screen. That's one of the most primitive things that you can interact with the user, right? I need to be able to put letters on the screen. So basically, the handler location is where the code is, right? Then once BIOS complete the hardware check, it would first thing would do is to load the first 512 bytes. So let me ask you this first question. How many lines of assembly you can fit within 512 bytes? Almost nothing, right? Let's assume that it's like a word. Let's say your instructions 4 to 8 bytes, right? Intel processor, it can have different size. 512 divided by 4, that's like 128 assembly line of assembly. That's not a lot, right? But it's better than nothing, all right? So what does this give you? So let me rephrase the question. What can I assume when I write code in C and I have a main function? When I run it, I'll start with the first line of main function, right? This behaves almost the same way. When I turn my computer on, that's my first line that I'll do. It gives me the ability as if this is the main function when I turn on the computer, all right? And these 512 bytes to be loaded at this address 7000. So the earlier address is used for the interrupt handler. So I installed the interrupt handler there. In case something happened, I know how to handle that. Then I load the first 512 bytes at 7C00. Then to actually go to the main function, I just jump 7C00. Simple, right? Every time you power on, that will be always the line, the first line to run. And during this step, the CPU is still running in a 16-bit mode. 16-bit mode means that instruction most of the time is 2 bytes. So you can fit in quite a bit of instruction. And then you have some region in the memory that you can access. How much? 16-bit means that my address is up to 2 to the 16 minus 1. Because I only have 16-bit to represent my address. So I have the memory address of 64 kilobytes. That's it. I only have 64 kilobytes to work with. And any valid bootloader code, you need to make sure the last 2 bytes is 0xAA55 at the end. It basically, that whole 512 bytes has to end with 0xAA55. It's just a signal to tell that, hey, this thing is not corrupted. This is a valid bootloader. You can use this code to boot the machine. All right. Any questions so far? Yes. Okay. So most of the time, again, the purpose is so that I can work with a better functionality. So what it does is it prepare because as you said, that's way too small. So the solution is I cannot launch all the process, start the kernel and make sure the kernel sits on top of the hardware and do everything. So I'll go to the second stage, bootloader. I'll very set up just enough that I can run the CPU not in the 16-bit mode, but a functional CPU with some basic functionality. What are those basic functionality? First of all, if you install multiple OS on your machine, what are you gonna be greeted with when you turn it on? Which OS are you gonna use right at the end? Those are something that the second stage bootloader gives you. It gives you the interface for the user to select, okay, do I want to open the Windows? Do I want to open Linux, which by the way, somehow I also install on my machine. It prepares for the actual OS, right? So here's an example of the Hello World bootloader, which doesn't do anything. Greet you with Hello World. That's it. Not useful, all right? But as you can see, it has to end with AA55. Okay? All right, but let's say the first stage bootloader is done. Then, as I told you, like the main thing the first stage bootloader do is first, I need to make sure I can use more memory because 64 kilobyte and 16-bit mode is too restrictive. I don't want that. All right. So I want more usable memory. I want to be able to make sure the user can select what should be my boot partition. Anyone try to install Ubuntu for the first time on your machine? You plug in the USB drive and it would ask you, right? Do you want to boot from the USB drive or from your hard disk? But both of them have the boot partition, which means that I can boot from those devices. All right. Then after these things are available, right? Then I can load the real boot code into the memory. That's kind of toward the end of the first stage bootloader. Then I transfer the second stage bootloader, which give you this interface that you can pick. Usually you have a default thing. So if you don't pick, it will go to the default most of the time your hard drive. So you have the USB drive on a machine that has Linux installation and the bootloader in there. you get to pick, and then the default, you don't do anything. Some machine would default to your hard drive. Now, basically, other things that you saw from the screen, right? At this time, I can also do like maintenance kind of thing, like mem check. Right? I can test my memory instead of going to the OS. But with this, now I can start my OS. So all these things is just so I can start my OS, because the kernel, which is the next step, the kernel is inside your OS, inside Windows, inside Mac OS, inside Linux. This is a part of your machine. It's more like a part of your machine, from the BIOS to the bootloader. Then the bootloader actually then will load the main OS. All right. So the next step is the kernel. What is a kernel? Kernel is basically the lowest level of software that would run on your system. Why? Why is that the first thing I should do? So that I can have, first of all, access to every single hardware from the kernel point of view. Now I have a piece of software that can control the hardware. And then the piece of software would open up system call where the application itself can call this thing. Basically, now I have a bunch of function calls. I say, hey, you can call me. And this function call is implemented by some engineer to control the hardware that prevents the application to have to control the hardware on its own. I just call like printf, for example, right? So at this step, right, basically you want to run the application and you have the hardware. The OS sits between that. Basically, the first thing you do, you have the kernel sit right next to the hardware. Now, both the rest of the OS can operate the hardware, and the application can operate the hardware. And one nice thing about that is, remember those virtual machines and other things? Part of the kernel task is also making sure you establish all those stuff with the hardware. So you have page table and everything. And then any random code that you don't even trust, like some random application, become untrusted. And then the kernel and the hardware becomes trusted. So let me ask you this question. What if a program got the kernel privilege? Yeah, it has access to everything. Fun. All right. That's fun in a bad way. All right. So that's why we should have a trusted trusted code inside the kernel. And people who can modify that and modify what the kernel wants should only be folks with the kernel privilege. So if you don't have the kernel privilege, it's okay. Most application doesn't have kernel privilege. And you want to make sure for your machine, you don't run application with kernel privilege unless you know what you're doing. All right. So now this is actually the time my operating system, which has been working so far. So you don't run any app so far, right? The only thing you run, bootloader, then the OS, then I established the kernel. This is just to make sure the hardware is ready to run your program. Then you can now run your program in a user mode while the kernel handle anything in the hardware in the kernel mode. All right, so we call this dual mode execution. OS can transfer control. Whenever you see this word control, it means that when like who is the one running, transferring the control in what is the code that you're running. That it's the same way as if you look at a program, you look at if else. Like that's why we call it control instruction. It dictates what line you're running in your program. So you transfer the control to the application. Application can now control the hardware. Application can now control the hardware. The problem is I still want to have a safe system, right? If my program counter, what's the program counter? What does it do? it points to the current line that I'm running. So every program becomes assembly, right? So it has to tell the CPU, run this line, then this line, then this line, then this line. That's the program counter. And let's say you have the application right here, right? Let's say you have the application right here. And you have the like app 1, app 2, right? And let's say application 1 say keep running everything here. How can I eventually know that app 2 will get to run? Because the control is with app 1, right? PC of app 1 moving and say, hey, keep doing this, keep doing this, keep doing this. Then it basically becomes the kernel job to make sure app 1 doesn't take over my computer. Let's say I am a bad guy, I write an application with infinite loop. I double click that application. Can I, in theory, run other applications? Yeah, I mean, my Windows can run like any number of applications. I can run Chrome, I can run Microsoft Word, I can run Spotify. I mean, Spotify might run into an infinite loop. Who cares? I can still run Microsoft Word and my game, right? I mean, think about it. Your game is basically one giant infinite loop until you hit the exit, right? So if you have only one single CPU, how can you enforce that illusion? Enforce the illusion that, well, Spotify is in the infinite loop. I want to make sure that at some point, I don't care what Spotify is doing, at some point, Microsoft Word can run. Basically, that's the job of the kernel. Kernel will come in and say, hey, pass the control back so I can give the control to the other application. Now, app 2 can run, right? So the dual mode execution allows the control to switch from user and kernel. So once kernel takes control, it has now take back the control, and because it's trusted, for now, let's assume that kernel is trusted, all right? You don't get hacked yet. So when kernel is trusted, basically, eventually I'll make sure everyone else can run. And how do I do this? Right now, this is a normal method to run an application. I have a program counter. I run that code, that line, then I move to the next line. The whole thing here is basically, once I finish this line, I move to the next line, then I move to the next line, then I move to the next line of the same application. All right. And at some point, this guy that used to point to app 1 need to make sure it now point to the kernel code so that I can give the control to other applications. The way I do this is the CPU would maintain a flag in one of the register that would set the mode of execution. There's also the virtual memory, if you remember from system skill lecture, that will also check any permission for the user versus kernel privilege. Then I have the application going this way, right? Keep going. I go to the next line. I go to the next line. I go to the next line. And let's say I want to switch the mode. Let's say I want to switch the mode. I would set the flag. I would then set the flag, which allow me to set the PC using the select mode, right? And the mode will come here, which allow you to set the PC, the program counter, to the kernel. And then from the kernel, if I reset the flag again, say, hey, I want to switch back to the user, then the kernel can change the PC to the user application. This allows you to switch between user and kernel by just setting this one flag. Whenever I want to change to the kernel, I set the flag. Whenever I want to change back to the user, I also set that same flag. Yes. Yeah.
Is it the same as being admin?
Kind of, but think about it this way. Kernel is like also a program that has to keep running to maintain the functionality of a computer, right? So it means that eventually I have to switch back to the kernel, so a kernel can operate the computer and then switch back to the user, right? So this flag would allow you to switch back and forth between running user application and running the kernel. Yes. Depending on who control the program counter, there'll be the code that would set the flag.
Oh,
There's also an interrupt handler, which can also kind of like you can interrupt to make sure the kernel take control. Have us? Blue screen.
yeah.
Okay. I hope I don't force kernel panic on any one of you guys. Okay, so when you are on the user mode, it basically means that I cannot execute privileged instructions such as access kernel register or directly access system register or adjust the page table basically, or change the interrupt table to have a different interrupt handler. I cannot disable interrupt. Basically, you should be able to just do what normal applications should be able to do, but not touching the system. That's multiple check, like virtual memory is one of the check. Back in the day, there's this thing called base and bound. When the virtual memory is more primitive, we used to have a region thing. This part of the memory cannot be touched. This part of memory cannot be touched because this part is used by X, this part is used by Y. We call this base and bound because you're trying to access this region, but your address fall here. It means that you have illegal access because your bound is just here, not here. That's why we have segmentation fault. The name segment come from base and bound. People will basically back in the day we use segmented memory. We divide memory into multiple chunks. Each chunk has the base, the starting point, and the bound. How far can you go? And that's a segment. Segmentation fault is when you're here, but your pointer point here. That's why we call this segmentation fault. That's what allows the kernel to take the control back. The timer interrupt. Basically, each interval set by the hardware, when that happens, I'll make sure kernel can run. Then the kernel switch back to the user if everything works properly. All right. During the kernel mode, if you have any interrupt exception system call, it gets handled during the time. It also maps memory region. Like I have new application that wants more memory. Basically, it's about managing the machine resources. It's about managing the machine resources and also manage weird things that come from your program, like divide by zero or seg fault. What do you do, right? So the kernel mode will kind of handle that. The transition is from the user to kernel, you can use hardware interrupts, which we've done asynchronously with caused by the hardware. I move a mouse, I hit something on the keyboard. So a pattern would cause the hardware interrupt to kick in. Exception like divide by zero or seg fault, these are caused by the program itself, would transition the user to kernel as well. Then the kernel is like, oh, what's going on? Let me handle that. System call, like file access. We access the file all the time, right? These are also done by I change to the kernel mode. Then the kernel handle system call, which then access the file. Yes. Question? Oh, okay. And then what we call these things like exception and system call, we call this a trap. Why? When this thing happen, we trap them so that we can handle them by the kernel, right? Then from kernel back to the user is when you're done with the interrupt exception syscall, you go back to the user. It's as simple as that. You can also switch to a different process. When app1 is running, kernel can choose to handle app2 the command keep running. Create a new process, run a new application, or that can be an app call. For example, Linux signal. We'll learn this in the next lecture. Oh, this lecture, I should forgot. I think it's the next lecture. Basically, it's a signal that your code can signal, and that would allow the code itself, not the kernel, to handle the signal. Another thing that would be a representative user level up call, interrupt, exception handler, for example. Try catch, right? Try catch is a part of your program, but that's an exception. Basically, it means that the user application, hey, I know how to handle this. Give me back the control. All right, it's as simple as that. I write the application and I know exactly what to do when I have divide by 0. So you let the kernel know, okay, I know that's an exception. I just switch to the kernel. I'll let you know also I know how to handle that. So give me back the control. So I can use the thing in try catch to get rid of, to handle the exception. All right. So in x86, to go into the kernel mode, the first thing you do is to mask the interrupt. Basically, you want to make sure you disable interrupt during the transition. Why? The transition is caused by one interrupt. If there's another interrupt happening, things get weird. Which one should I handle? So I disable it first. Then I save the CPU state. Whatever I'm running on the application right now, because I'm about to switch to the kernel, I need to save the progress. It's like when you're playing a game, you walk into a different room, you want to save the progress because you're doing something else. What are the states? What's on the stack pointer? So that when I resume, I can have my old stack back. Execution flag and instruction pointer. Instruction pointer is basically the program counter, right? Then I switch to the kernel stack, which has its own register. Now I know where the kernel stack is. Then I push the CPU state from step two, and any CPU state you want to push in, put that on the kernel stack. You can also push error code on top. Then you invoke the interrupt handler. So I have more diagram to show this process. All right. Basically, the handler then must save the state using the push AD instruction. All right. So here's how things are handled. So I have a program called foo, and inside foo, there's like a while loop with x equal x plus 1, y equal y minus 2. Something really simple, right? The right side, I have the handler. And right now, I have this state, the stack pointer. ESP is a stack pointer. It points to where my top of my application stack is. Again, remember this skill lecture assembly, that stack, the stack thing that we talk about. That's the stack pointer. EIP, instruction pointer, that's the program counter. I need to save both of them to resume. And if I don't have the program counter, and when I handle the interrupt, I don't know where to go back to. So I need to save them. So the first thing is, I would save these things, the stack pointer, the program counter, on the interrupt stack. When I handle the interrupt, this is the stack pointer. This is the, these two things. The stack pointer, and then this is the program counter. So now I know where to go back when I'm done handling the interrupt. And also, when I go back, I have all my state of the stack back. I know where is my stack. Basically, when I have the interrupt, the kernel have to remember this location and this line that is right after the interrupt happened. So that when the interrupt is done, I can go back and resume execution. Think of it as a function call. Remember function call in syscale? Same thing. But now you have the interrupt stack and you put it on the interrupt stack. All right. And then the next step is anything that are on the register, when you're running the application, save it here so you can handle when you have to go back to the application so that you can resume the execution with the state, with whatever should be in the register. All right. And then to restore the process, because now everything is safe, right? Then you use a pop add instruction, which will pop, but instead of popping on the user stack, now you pop on the interrupt stack. Then you can restore using the iReturn. iReturn will basically switch the CPU from kernel to user and will restore that exact line where you were running when interrupt happened. All right. Then system call is basically it's a thing that will provide the illusion, right? That the kernel is just about a lot of libraries that you can call. The user doesn't have to know how I implement the kernel. The system call say, hey, these are the things you can do. File access, printing things. These are the syscall. Then when you call these functions, it traps. Basically, it creates a trap that allows the kernel to run the syscall. The kernel will basically run that system call on behalf of the user application. Why is that useful? Again, kernel control the hardware. My syscall wants to do something with the hardware, like access a file. So I call that function and let the kernel handle the job. All right. So when this thing happen, for example, I want to open a file. When I want to open a file, right? The first step is I would basically handle using the user stuff. And inside that, you might note that I have the same function call, right? The same function call. Then I push the syscall into the stack. Then I trap, which means I handle the syscall. Then I handle the syscall. Now with the hardware trap, it trigger the kernel stuff. It triggered the kernel stuff, which at this point, because it's a file open, right? Because it's a file open, it knows, okay, kernel C file open. Then it look into the file open handler, which already pre-written to open the file for you. Now it takes the argument, actually open the file, right? See how this is the same function call, but because it's run by the kernel who have the right privilege to touch the hardware. So basically what I do is I take the argument from the user, then call the file open, so that I can handle that and return. Now, inside the kernel, I run this function called file open. I do whatever operation I have to do. When I'm done, I'm going back to the kernel stuff, which then return the trap. Say, hey, I'm done. When I return the trap, I'm done with opening the file, right? Basically, this whole trap thing allow syscall to be handled as if these are interrupts. You push the system call, then you trap. The hardware, once it's got the trap, it knows, okay, these are the system call I have to do. Based on the arguments, I will call my own implementation of, in this case, opening a file. So it then can open the file and then return the data back. Basically, now it's a file descriptor, the pointer to the file back to the user application. And then that's the stop on the user land, right? Basically, you would assume that the caller would, for example, put the file name in there so that you can actually like open the file, right? Then you put the code for the system call we want into EAX. See? System call open, and you put that into EAX. Then you trap the kernel and return. Your user part is pretty simple. Then you trap, then return. The kernel part, once I have this, right? There'll be a function to open the kernel stub and then check the stack pointer. And oh, who is calling? Who's making this trap? Who's making this trap? And see if it's valid. If it's not valid, the first thing is return some error code because your call is not valid. If it's a valid call, then you use the user stack pointer, try to access the file name. Try to access the file name. And then you try to actually get the file, right, to open. And if it's like if there's any error in using the file name, right, in using the file name, then you also then return the error. So the first error is about address range of where you want to access. The second error is like file name. There's something wrong with the file name. Then if everything is correct, I will call kernel open, which is basically opening the file with the local copy that now I have to access with the file name. This is like a bunch of process that the kernel has to prepare to open the file so that you can return the file pointer, for example, in the C code. All right, just a quick thing called threaded OS that I don't think we have enough time because I want to go to I want you to check this first. The first activity bootloader is already on Canvas. Check it out. You can click on this. It will go to YouTube.
So remember back to my first video where I said that I was too cool for 3D engines or
which I don't think you can hear this, but the whole thing is like the video maker is basically built an OS that only runs Turtles. And the video can go through the example. Feel free to check it out because again, do this first and be aware that assignment 1 is up. So check it out, read the assignment so that you can gauge like how much time you have to allocate for the assignment. Do this. All right. So that's the end of the lecture part. Now basically in the activity. Yeah. So I'll stop the recording. Feel free to ask me anything about the activity.